About the tale of two packets. Really what I'd like to do here is walk us through a scenario watching two packets, Bob and Sally, as they traverse the network. Now what my hope is that as you walk through this video, you're not going to see anything new. You're more so going to see all of the concepts that you've seen on the basic TCPIP sections up till now put together in one nice flow from end to end. Let's start off with the rather short story of Bob. Bob is our local boy packet, meaning that he is a packet that originates on a network segment and stays on that network segment. He represents local communication, maybe moving from this computer right here down to this computer right here without ever leaving the local network. Now what I'd like to do is zoom in on this part of the network so we can watch the story of Bob unfold. There we go. Now that we're zoomed in, we can see all the IP address and MAC address information for that left side of the network that the packets are going to travel on. Now for this short story of Bob, we'll assume that the traffic is going to come from 172.10.1.20 and go down to 172.10.1.30, this host down below. So going from this guy to this guy. Now Bob represents a ping packet. So up on this computer up top, we opened a command prompt and type in ping 172.10.1.30. Here's what happens. The host up top looks at the address that you're trying to access, or the address we're pinging in this case, and it says, okay, 172.10, I'm writing it up above, .1.30, and I'm going to compare that to my IP address. Now notice at the bottom I put assume the subnet mask in this scenario is 255.255.255.0. So it looks at it and says, okay, we're both on the 172 network since that's the first portion of the subnet mask, first 255. We're both on the 172.10 network, that's the second portion of the subnet mask, 255. We're both on the 172.10.1 network, because that's the third portion. Remember, 255.255.255 represents the network. Now the 0 in the subnet mask represents the host. So this guy's saying, I'm host 20 and I'm trying to access host 30. Immediately, what he realizes, this top computer, is that the computer I'm trying to access is on the same network as myself. I'm not going to have to go through a router to get there. That's why we called this the rather short story of Bob. He's the local boy. So this computer says, well, if that computer's right on my same network, I need that computer's MAC address because I'm going to need to send this into the switch. And by the way, that's what this line represents here. It's a switch or a hub that all these devices that are plugging into. It's the same local area network. So it says I need that MAC address, and what I'm going to do to find it is I'm going to ARP. ARP, just like a dog, it barks out the address resolution protocol. It's a broadcast message that goes everywhere on that network and says, hello, I am looking for whoever has the MAC or whoever has the IP address 172.10.1.30. Now, everybody who's plugged into that same switch or that same hub gets that broadcast. It comes out here to the router and he gets it and looks and says, oh, it's looking for the MAC address of .30. Well, I'm not .30, so I'm not even going to reply, and it drops the broadcast. It goes out here to some other computers that are on the network. They get it, they drop it. This guy gets it and he realizes, oh, that's me. I'm the .30. So I will reply back up to that host directly. It's going to send a message directly back up and say, hi, I'm 172.10.1.30, and my MAC address is AA00BC333211. Great. The host up there receives that and says, now I've got the missing link, the missing layer 2 address, data link layer address, that I can fill in the packet. So it puts in the packet. If we were to look at the packet, we have the data, that's Bob. It's the ping message saying, hello, are you alive? And then we have the port number information, the source and destination port. We have the source and destination IP address, which is going to be, the source is the .20, 172.10.1.20. Destination is .30. The source and destination MAC address, that's going to be tacked on the front too. The source will be the long MAC address right here, 3923 is the last 4 digits, and the destination MAC address will be 3211, and that's what it found out from the ARP. With all those headers put onto the data, it will then send that message out its network card to the switch. The switch receives it and says, oh, you're trying to go out that port, because it knows what MAC addresses are on what ports, and the computer receives it. That is the end of Bob. Bob has been received, all the headers stripped off. He's processed, and the machine down here will send a reply ping saying, yes, I am alive. The story of Sally is not as simple as it is for Bob. Sally is the same kind of packet as Bob. It's a ping packet, but it's going to be coming from this computer over on the left-hand side, same host, 172.10.120, but that host decided to ping 192.168.0.100. So at this point, Sally is going to have to cross, that's the Sally packet, it's going to have to cross the whole network, router by router, to reach that server on the right-hand side. What I'd like to do is zoom in, just as we did with Bob, on this portion of the network first, then we'll watch Sally as she goes from device to device. Now that we're zoomed in, we're at the host 172.10.1.20, this guy right here. And we have Sally who said ping 192.168.0.100. So again, same as the Bob scenario, we're assuming the subnet mask is 255.255.255.0. So first thing the computer does is says, okay, well, let's line it up. 192.168.0.100. Let's compare networks. I've got 192 and then I've got 172. Okay, right there, stop the train. That IP address is on a different network than me. It doesn't even have to look at the rest of it, because as soon as it sees 192, it goes, aha, this is not on my network, which means Sally is going to be a completely different story than Bob. Because this computer realizes that it can't just send out an ARP message saying, hello, what is the MAC address for 192.168.0.100? Why? Because the ARP message is a broadcast. It goes to everybody until it hits a router. The job of a router is to stop broadcasts. So that broadcast will reach down here, it'll reach over here, saying, who is 192.168.0.100? And the router receives it, drops it, because you are not allowed to go past this point. Broadcasts end here. Otherwise, the network would just constantly be flooded with all kinds of broadcast traffic if it was allowed to pass through routers. So the computer realizes I will not be successful in ARPing to get the MAC address of the server that's way over here on the other side of the network. So here's what it's going to do. It's going to put Sally inside of a packet, that's our data, the ping message. It's going to have the port number, the source and destination port number, just like it did for Bob, dictating what service it's trying to look for. Then it's going to have the source and destination IP address. Now, the source IP address is going to be 172.10.1.20. That's the PC that Sally originated from. The destination IP address, the one that we're going to, as you might expect, is the server. 192.168.0.100. Now we come to the big part of the puzzle. What MAC addresses are going to be filled in there? Well, the source. See if you can figure this out. I challenge you. Pause the video right now. Go ahead and, well, not right now. Pause the video and tell me what source and destination MAC addresses do you think will be in the packet? Go ahead and pause it right now. Okay, you've unpaused it. Or you're just too lazy to reach out for that mouse. The source MAC address is going to be the MAC address of Sally's PC, 342F39BC 3923. The destination MAC address will be the MAC address of the router. See, here's the picture. As soon as this PC realizes that Sally is not destined for the local network, it's going to send out an ARP message for its default gateway, meaning the router that enables it to get off of the network, because it assumes that the router will have a good idea of where all the IP addresses in the world are. And as we will discover as we continue throughout this series, that's what routers do. They help you find where IP addresses are. So it will send out an ARP message, but it won't be for 192.168.0.100. It'll be for its default gateway, which we assume from this picture, it's 172.10.1.1. The router replies to that ARP and says, here's my MAC address, and that gets filled in as the destination MAC address. I'll just put the last four digits, 3212, as the MAC address that the data will be sent to. So Sally is sent out of the PC, received by the router. The router looks at it and says, okay, this is for my MAC address, so this is meant for me. I'll pick it up and process the packet. Then it looks at the IP addresses and say, okay, it came from this person. I know that person. They're plugged into the same network. I recognize their address. But it looks like it's going to someone that is not on this network. And it's definitely not me. That's one of the questions the router has to ask. Are you trying to access me, or are you just trying to go through me? It looks at that IP addresses and says, well, looks like you're trying to go through me. Back to our roadmap on the story of Sally. I don't know why, I just had this random thought, but do you guys remember this game, Ghosts and Goblins? This is a game that I remember from my younger days, and I used to love this game. It's where you had the little guy with the armor. You see him, I don't know, it's kind of small, but you see the guy right over here, and he's got the, where's my pen? The armor that he's wearing, and like if you get hit by one of these ghost or goblin, he kind of gets hit and his armor all flies off, and he's standing there in his underwear with the sword, and you have to get armor back on, and you know, if they hit you again, you're gonna die. But anyway, my point in bringing up this game is cool. It was, in my opinion, way ahead of its time, because you would be going through fighting these ghosts and goblins on a level, and once you completed the level, it would kind of bring up the big map, the big picture of where you are, and it would say, okay, you've completed the dungeon's door or something like that. Now you're moving on to the pinnacle peaks of death, and it would show you where on the map you were. That's what we're doing here. Long story for a short picture. We've got the story of Sally. We have completed this level. The router has now received the packet, and now we're moving on to the next section of the map, which is this group of routers. So let's get our bearings. This router over here on the left-hand side represents the router that was the PC's default gateway. If we were to finish the network diagram, the PC was sitting up here. There was the line that would connect down here to this router. 172.10.1.1 was that default gateway. It just received the packet and realized this is not a packet for me. It's going to 192.168.0.1. So it looks at its routing table, and the routing table is everything that makes the router what it is. It tells it where all the IP addresses are, and it says, oh, well, I'm not plugged in to a network that is 192.168.0. something, but I'm looking at my routing table, and it's telling me that I need to send the packet to this guy, 10.10.1.2, because that guy, that router, has the ability to get me to the 192.168.0.100 network. So what it does is it takes that data. There's Sally inside of the packet. It's the ping message. It's got the same port numbers. It doesn't touch the port numbers, leaves those the same. Looks at the source and destination IP address and does not touch them. Source and destination IP address remains the same because it doesn't want to forget where it originally came from and where its final destination is. But the source and destination MAC address, now that is going to be a different story. It literally gets ripped off, torn off the packet as it passes from this network to this network. The new source MAC address becomes the MAC address of this router. We'll call him router A. The new destination MAC address becomes the MAC address of router B, because that is what allows the packet to travel across this link and be received by this router down here. Now, let me put a side note in there for some of you that may have a little more experience with networks and be questioning me right now going, wait a second. I will mention that MAC addresses are an Ethernet technology, meaning there's only a such thing, if you will, as MAC addresses in the world of switches and hubs and PCs and network cards and so on. Once you move from the LAN environment over here into the WAN environment, the wide area network environment over here, and you start getting into these things known as serial links, we actually leave MAC addresses behind completely, and we'll be moving into new kinds of addresses. But what I want to do for now is push that. That's actually at the very, very end of this entire series. We're not going to get into the WAN technology and what those addresses are, so let's just assume that they are MAC addresses. Router A will put itself as the source MAC, and router B will become the new destination MAC. The packet will travel across the WAN link and be received by router B. Router B looks at it and says, oh, well, this did not come from my source IP. That source IP must be somewhere over here, because that's what my routing table tells me. And it's definitely not destined for me. You're just trying to go through me. So what I'll do is I'll look at my routing table and see how to get to the 192.168.0 network. As it does, it realizes that I need to send the packet upstream to the next router. My routing table told me that. So my next hop IP address is going to be 10.5.1.2, but I'm not going to change the IP addresses in the packet. Again, everything stays the same in that packet up to the source and destination MAC address. Again, as soon as this router receives it, it rips off the MAC address that was used to communicate between here and here and replaces it with the MAC address itself being the source, router B, this interface, and the router C we'll say in this picture will become the new destination MAC address. Replaces those MACs, send the packet, router C receives it, same story happens again. I'll save you the pain of seeing one more slide like this because all that would happen is router C would just tear off these MAC addresses that are used between communication on B and C and replace it with the MAC addresses that are used to communicate between C and D. So we'll just assume, follow this train, C sends the packet to D, D receives it, and D is the one that is connected to the network that the server is really on. So as soon as D receives that packet, it looks at the source and destination IP address, and we'll just say Sally, the data is right there. There's the port number, source and destination IP address, and it says, oh, well, you came from that side of the network over here. Here's router C, here's D, and you are going to the destination IP address 192.168.0.100. Looks at its routing table and says, oh, well, I think I can help you. I am connected to the 192.168.0 network. It's right out my Ethernet interface. So tell you what I'm going to do. I'm going to strip off the source and destination MAC addresses that allowed the message to get from C to D. And I'm going to replace them with my source MAC address, which is the one connected to the Ethernet port right here. And I'm going to ARP. I'm going to find out what the destination IP address is of 192.168.0.100. Hold on one second. ARP! An ARP message yells out, goes across the network, and is received by everybody, including that server, who says, oh, that's me. Let me respond. Responds and says, here's my MAC address, at which point the router fills that MAC address in as the destination and sends Sally the packet humming out into the switch, which reaches the server. Destination reached. The server tears off the source and destination MAC, the source and destination IP address, and says, aha, I am the final destination, looks at the ping message and says, oh, you're just trying to ping me. Let me respond and send a message all the way back across the network to the original source host that issued this ping message so that they can know that I received the message and I transmitted something back. Tell me it's not amazing to see that whole process, and then to think that when you go to a website and you're watching that page just load up with graphics and images and text, you're getting hundreds of packets from all over the world that aren't just 4 router hops away, like we saw in this example, but they might be 10, 20, 25 different routers that you're going through to reach that final destination. And we get antsy if it starts taking 2 or 3 seconds for that web page to load. We're kind of like, man, what's going on? But if you really think about what's happening behind the scenes, I'm amazed that it doesn't take hours for a web page to load. Check this out. I'm going to bring up, I have a connection over here to my firewall. I'm going to just do a command that does a trace route to www, let's go to cisco.com. This shows me every single router along the way that I'm going through to reach Cisco. First router was phoenix.cox.net. That's my ISP. Second router, third router, fourth router. Every single one of these. I can see that I'm still in Phoenix. Oh, left Phoenix into, looks like Los Angeles, somewhere around there. You can kind of tell where these routers are. And somewhere I received, I entered into Cisco Systems router at packbell.net, which I'm assuming that's their ISP. And went through a couple more routers. 11 routers later, I didn't reach my destination. I reached a firewall because Cisco doesn't want my little exploration packet to go beyond certain points in their network where their internal network might be exposed. So they told their firewall, well, when something reaches this that's trying to trace the route into our network, go ahead and block it, because you can imagine that's a security vulnerability. But every single one of those 11 routers went through exactly the same process that I just showed you, stripping and replacing those layer 2 headers the whole way across. Thus ends the tale of the two packets, Bob and Sally. Bob being the local boy packet that just had to send an ARP message and reach something on its own network, and Sally having to travel across the world through routers to reach her final destination. One thing I will say is understanding the process that we just went through, how those layer 2 and layer 3 addresses help our packets reach their destination, is absolutely critical to your ability to be able to troubleshoot when something goes wrong. I'll show you later on as we get deeper into the series packet sniffing, where we can actually capture packets going across the network and exposing what's in the header. We'll actually be able to grab packets and look at what's in that header information. If you understand this process, that header will make a lot more sense. Well, I hope this has been informative for you, and